It's good to be almost the last talk because many of the topics that I need to use during my talk is already covered by many of the colleagues. More specifically in this talk, I'm going to refer to notion of concept-based explanation that was covered by one of our colleagues, I guess. Julia and Wednesday discussed it. So the general idea of this talk is mostly about model explainability. There are always tension between interpretable by design versus post hoc explanation. And this is the decision that is usually made by practitioners at the beginning. So this talk is about bridging the gap between these two paradigms. And more specifically, I'm going to talk about method that tries to incrementally carve out a symbolic model or interpretable model that is hidden inside of these black boxes, and as a result, make these black boxes incrementally to white boxes. So why do we need model explainability? Of course, one of the most important aspects of that is trust. When the objective of training side is different than testing side, and you want to relinquish the control from clinician to AI, it's important to understand what is happening behind the scene and what is the mechanistic decision-making of the AI algorithm. It is important from causality point of view. All of these machine learning methods are encoding correlation. But what if we can use this to generate hypotheses that we can collect more data and can be tested formally? For example, in this paper that was published, I guess, this year, the authors used this model explanation in order to have better understanding of mechanistic insight about the genetic process of the disease. It is also important in terms of transferability. For example, when you have a model that trained on one side and you want to deploy it on another side, clinical rules are very transferable. Castrogenic recess is always associated, for example, with a specific disease, regardless of the hospital. This is not so much the case about our AI algorithm, when we have to force them to make this interpretable. Is it possible to use model explanation to carve out more transferable algorithm that is generalizable from one side to another one? And this is one of the focus of this talk. It's also important from informativeness. If the AI is part of the decision making, a yes and no answer is not sufficient. An AI algorithm should be able to explain its decision so that it can provide more information for the clinician who's going to make a decision. And of course, if we are interested in deployment of this algorithm, we have to worry about the ethical aspect of this model, and we should be able to audit this model. So we have to go beyond performance metric area under curve and so on and so forth, and be able to audit this model. I have to say that the ethical implementation of AI goes beyond, way beyond algorithmic fairness, but that's a different topic. Okay, so what are the general design approaches when we want to develop this AI algorithm specifically for healthcare or for any others? Usually the approaches are twofold. Either you go with the black box method and you do post hoc explanation, or you design a method to be transparent to begin with. And these are currently, this is the design choice that you make at the beginning. What are the examples of the post hoc explanation? There are multiple choices for post hoc explanation. One of the most popular approach in post hoc explanation are feature attributions. What is the idea of feature attribution? This way or the other, feature attribution associate feature importance to input. For example, a GradCam may associate relative importance of the pixel in the final decision-making of the AI algorithm. The transparent model or interpretable by design approach, comes in different flavor. One of the most salient examples are rule-based methods. So these methods are interpretable by design. There are pros and cons into each of these approaches. Post hoc explainability don't compromise in the term of performance of the black box. You can choose any black box that you want and do post-hoc explanation. As a result, you don't experience any dip in the performance. However, it usually leaves too much of the explanation to the human. And human interpretation is subjective and also vulnerable to confirmation bias. There has been several studies that shows that it may result in inconsistent explanation. For example, in this work, the author showed that if you change the explanation for one class versus another one, the interpretation does not change that much. That leaves so much of interpretation to the eyes of human, it makes it very subjective. Also, it is subject, there is no recourse. So for example, if you don't like some property of the AI algorithm, you find out that it's focusing on something that it shouldn't focus, what do? You have to somehow retrain, recollect the new data, or come up with a new algorithm. Transparent model, on the other hand, or interpreter by design model, on the other hand, I'm going to use this transparent versus interpreter by design exchangeably, offer recourse. So if you don't like some of the rules in your model, you can go and manually change it. This is the advantage. However, there are limited design. The design of the interpretable model are quite limited. It is usually used for tabular data. There are, of course, approaches to deploy that for images that I'm going to allude to that in the following slide. But overall, the designs are very limited. And because of the limitation in the design choice, usually you suffer from performance, dip in the performance, when you compare those two black box algorithms. For example, in this slide, I'm showing the performance of one of the most common concept-based approach in the context of X-ray classification of the disease. And you see that when you compare to black box, there's a significant performance across multiple classes. So what are the desirable properties that we want if you want to build a new type of approach? We like the performance of the black box approach. We like that they are very flexible and can result in good performance. So we don't want to compromise on the performance. But we also like the recourse aspect of interpretable model. We want to be able to go and change some of the properties of the model if we don't like it. We also like the transferability aspect. At the end, clinical rules are invariant from site to site. We want to have similar properties to get from this new approach. So, what do we mean by rules? So let me give you an example of the rules. For example, for diabetes, one rule may say that if A1C test is more than 6.5% in first and second visit, it might be diabetes. The second rule might be saying that if random P glucose level is more than 200 and there is a hyperglycemia, which is frequent urination and increase in thirst and unexpected weight loss, it might be diabetes. So you can write this as a first order logic. So it usually comes in a form of P implies Q, and then P can be lots of and or. So the idea here is that we want to learn these rules that looks like a first order logic, this P implies Q, in a way that is related to some symbol that is understandable to human. We want to extract those from our black box. The idea here is that the general idea is as follows. We hypothesize that some of these symbolic rules are already hidden inside of the black box, and we want to discover it and extract it from the model. So what if we are able to carve those out from the black box and come up with a new symbolic approach? What do I mean symbolic? So we extract the symbols, which are concept, and the rules that combine them, which is comes in the form of first order logic, and carve it out from the black box. Now black box focus on a smaller number of samples, and we can continue this process in an incremental way, such that in each increment in this process, the contribution of the black box increases, and we come up with more rules. Is the general setup clear? OK. So now, in the following slides, I'm going to tell you how we are going to do that and what is the general setup. So the general setup is as follows. So we are assuming we are going to solve this problem in the context of medical imaging, but for sake of explanation, I'm going to use these typical computer vision examples because of the broader expertise of the audience is easier to convey. So we are assuming that on a training data, we have access to the, of course, images and final prediction, but alongside with that, we also have access to some human understandable concept or symbol. I'm going to use these two words, symbol and concept, exchangeably. So for example, in this case, the concept can be thin ear, shortened muzzle, round feet. We have trained a flexible black box of your choice that trains on input and tries to predict output. And we are assuming that this black box comes in a form of that you can think of it as a two function composed with each other, which is basically include any neural network that you can possibly imagine, regardless of the architecture. You can think of this that like initial layers extract some low-level information that you can somewhere can be abstracted into concept. I'll tell you how we can do this. And the final layers, perhaps the last layer or last two layers, learns how to combine them with each other. That applies to a convolution-based approach. And like if you're familiar with the transformer. In fact, all of these neural network approaches can be viewed as a composition. So we are viewing the initial layer as a feature extractor and the final layer as a combination. How we do that in the context of medical imaging? In the context of medical imaging, we are assuming that on a training data, we have images alongside with the radiology reports. And we are using natural language processing pipeline to extract concepts from radiology reports. These concepts are radiology anatomical mention in the radiology report and the pathology that are associated with those regions. There are relatively mature natural language NLP pipelines that can extract those. They are noisy, but they are working relatively well. So all in all, our training data consists of images, the final diagnosis, and these concepts that are extracted from radiology reports. Is the setup clear? OK. So how do we discover this concept from this pre-trained neural network? A very common approach is to basically cut the network in an intermediate layer and then learn a simple linear classifier that projects everything in a space of concept. It's as simple as learning a linear classifier that here I denote by T. So here these toggles represent presence or absence of a specific layer, a specific concept. So you can easily train a simple layer neural network and say that for each instance, what are the concepts that are present or absent in this layer. Now, what do we do with this concept? The general idea is as follows. When we discover new concept, we have to fit a first-order logic into this concept to mimic the behavior of the classifier. For the people who are familiar with the term distillation, the idea here is that we have a black box, and you're distilling the behavior into a symbolic model. That's the idea. So, but you can think of this as a way that you discover concept and you find a function to combine them so that it mimics the behavior of the classifier. However, these symbolic functions are usually very simple rules that does not apply for the entire data. So we borrow idea from so-called deferral model. So let me tell you what is a deferral model. So let's say that you develop an AI algorithm to be deployed in a clinic. And it's supposed to work alongside with clinician. So deferral model can be viewed as a selector or as a classifier that makes a decision when the decision has to be made by AI and when it has to be done by human. So when it is very confident, it let the AI to make a decision. Otherwise, it defer to human. So for us, this deferral model are making decisions between symbolic approach and a black box approach. So, and it has a budget, let's say 10%, and says that at least for 10% of the data, symbolic model should make a decision. If you're not confident, let the black box make a decision. So as a result, the black box focus on the area that is very certain about it. So all in all, in each step of the algorithm, you learn a first order logic function and a selector that decide that when this rule applies and when you're uncertain and let the black box should make a decision. So for the remaining data, we just copy the initial layers and fine-tune very last layer, which is very quick. And we repeat this process. You come up with a new classifier that is now focusing on the remaining data. And you can repeat this process again. Extract the concept, train a new symbolic model and deferral, and continue this process. And in each step of the process, the contribution of this black box reduces. Because in every iteration of this algorithm, you develop a new expert or new symbolic approach that focuses on new area of a data. So, yes?
I have a question.
Sure.
How do you define concepts that need to be defined for the initial layers? You said that we need to train on discover concepts from neural networks. Like
Yeah.
How do you define concepts in different modalities?
So as I mentioned at the in a setup, I'm assuming that the concepts are given to you, or in specific application that we have, we parse it from radiology report.
Okay, but you need some other kind of, I don't know, model somewhere to understand what concepts are there.
Yes.
Train that function.
Yeah. So from NLP, you can easily, this is basically is a very simple parser that like we know that specifically this word is anatomical mention, this word is pathology. So we parse that and create a concept. So it's very domain specific. It's for your domain, you know that what are the important concepts.
Okay, then let's say for pathology, I don't know what concepts are there.
I mean, if you don't know what is the concept, like you won't be able to convey it. So you need to work with the clinician, say that what are the important concepts that you make a decision based on? Because at the end of the day, we want to build a model that we're able to interact. If your output is just heat map, you won't be able to interact. Yes?
Also, I didn't get this stepwise approach when you were saying that the model is getting used somehow, the different model.
Deferral.
Yeah.
Okay. So do you understand like how we extract the concept?
Yes.
Okay. So when you extract the concept, I'll get back to you. Yeah.
Say again, in what sense you have residuals? Is this the information that's not explained by the interpretable model?
That's right. Yeah.
Okay.
Yeah. So you extract the concept, and this concept is a set of zeros and ones, multiple 0 and 1. So you can say, like, how do I combine these 0 and 1s, which are at the end probabilities, not exactly 0 and 1. How do I combine it so that it mimics the behavior of the black box, right? So you have to combine it, because you have set of 1s and 0. So one of the way to do that is to come up with a function to combine this to create the final output that looks like a black box. We adopt the first order logic specifically because many of the rules in this clinical decision making looks like that. Yeah. Do you have another question? Oh, you
I have another. So you're using the same concept as at each stage, right?
At each stage, yes.
Okay. So did you say that at each stage you're learning something different, or did
Yeah.
you,
Yeah.
Okay.
So but the concept projection doesn't need to be different. It's the concept projection, you do it only once.
Okay. But when you use the same concepts at each stage, how can you be so sure that you're learning something different?
Because this is because of the effect of deferral rules.
Oh, okay.
So the effect of deferral, and also in every iteration, your black box changes.
Oh, okay.
Because in initial one, you start with this, and on the remaining data, you fine-tune the last layer. So you have a new black box now.
Yeah, okay. Thank you.
Yeah. Any other question? Cool. So at the end, these G1 through G3 are set of experts that each of these experts focus on one area in the data. So you come up with a mixture of experts. So for the people who are familiar with non-parameter Bayesian approach, it is very similar to stick breaking. So every time you break the stick, you remain with the rest of it, and you continue this process until the last part is not breakable on a high level. And then if you combine them, you can create a mixture of this, that each mixture focus on one area of the data. OK, so let me give you some toy example. If just for illustration purpose, if you train this on a BERT data set for which you have the concept, and the concept in a BERT data set are things like color of the chest, color of the wing, shape of the beak, et cetera, et cetera. So the initial expert or symbolic approach come up with the rules such as like olive-sided fly catchers should have a breast color gray and a tail solid tail which has a solid pattern. But this only explains some part of the data. Another one says that it might have a color gray, but also wing should be gray, et cetera, et cetera. And at the end, you reach out to some subset of the data that are unexplainable, perhaps because the shades and like illumination is not good enough to detect the concept confidently. So you left at the very end with some of the part that explanation is not very confident. So on a toy data set, we applied it on two different architecture as a black box, traditional ResNet approach and recent transformer approach. The horizontal line represents the performance of the black box, and the red represents the performance of the method. You want the performance to be as close as possible to this black box, only on a symbolic part, because you can still use the last residual and then catch up with the black box approach. So the other two bars are performance of the classical concept-based approach. And you see that there's a significant difference in terms of performance. The gap is much wider. So the take-home message is that regardless of the performance of the black box, you can carve out a lot of explainability method that explain the decision in a very simple way, in a simple function. On a chest X-ray, for example, I'll just show you some simpler example. Like, for example, 1x1 for pleural effusion says that it's either on the left side or on the right side, or there is a hydrothorax, which is usually referred as unspecified pleural effusion. And like different experts make it more specific. What we saw empirically was that usually the initial layers of the symbolic model focus on easier samples, and then samples become more and more difficult, and the expert or the symbolic approaches start focusing on a subset of the data. And I have to say that in each step of this approach, you're reducing the training data, because each of those are associated with one symbolic function, or one first order logic function. And then you have smaller and smaller data to learn your symbolic, so variance increases and the model becomes less confident at some point, say stop, because I cannot reach the budget that you associate with me. And that's the place that you stop. And you can combine all of these rules on a class level and come up with the rules. For example, it says that edema should not have a tube, and like you should have a castrophenic recess, and so on and so forth. You can study that at the class level. And a similar story also for chest X-ray. So if you're looking to the classification of pleural effusion and pneumothorax, and horizontal line is the performance of the black box, blue is representation of our approach, and red and green are classical concept-based method, and you see that there's a significant difference. So one of our goal was not to compromise on the performance of the black box. And by using the black box and extracting features from it, we were able to achieve that. But one of the things that I mentioned at the beginning was transferability. Like we like the transferability aspect of the clinical rules. So for example, let's say that you train a model, let's say on a data mimicked from Boston area, and you want to deploy it on a data set from Stanford. The classical approach is the fine-tuning the model. You get the label data on your test on your target domain, and you fine-tune this model. So here, the idea here is that if you truly learn the clinical rules, it should be transferable. So you should not need to change that. So what don't we like about the current fine-tuning approach? It needs a lot of data on the target domain. It's computationally data inefficient, but we want to leverage this fact that there are rule-based approach, and presumably this rule-based method are transferable from one domain to another domain. Now the question is that how do we do this fine-tuning? The main issue is that usually on the target domain, you may not have the concepts. You may only have label data on a very small subset of samples. How do you fine-tune this model? So the procedure is as follows. We are going to deploy our mixture of rule-based approach on a new data, and we are assuming that on a small subset of those we have labels. We go, and for some of those we are correct, the model is correct, that here represented as green. For some of those are incorrect. We go and look at the concepts that are extracted on a correct classifier because the rule applied to those samples. And for the rest of them, we don't know what's the label for the rules. So as a result, we end up with a semi-supervised approach because on some of the samples in the test domain, you have the label, you have the concept. For the remaining one, you don't. And all you need to do is fine-tune your concept extractors, which is like simple linear layers, very fast. So the general setup is like this. On a small subset, you don't really need concept on the target domain. You go on, you get a label on a small number of subset samples on the target domain, just run it, you see where you are correct, where you're wrong. On the one that you are wrong, you look at the concept and then you propagate it with respect to rest of the concept. That's it. And how do we do that? All you need to do, you just need to fine-tune the last layer, which is a simple linear layer. You keep the rules the same, and you only fine-tune the concept extractors, which is like simple fine-tuning. So basically, the initial layers that we only need like one or two iteration, and the router, because now it's a new distribution. So here is some performance results. On the x-axis, you see the percentage of the training samples that you need to obtain on the test data, 2.5% of that all the way to 15%. Gray, or here represented by BB, is the vanilla transfer learning. And the blue is the result of our method. We can ignore the others one. These are other ablation studies that we have done here. Is that you can see that with a smaller amount of data, you can achieve much higher performance. So it's, in terms of data, is a very efficient algorithm. Y-axis is the performance. And here, this flop shows the computation. So here's the log. The y-axis is log of the flop. So you can think of it as like amount of computation that you need to fine-tune your model. And x-axis is, again, the same thing. 2.5%, 5%, 7% of the data is labeled. And notice that it's the log of the flop. So the lower, the better. The gray is the result of vanilla transfer learning, and the blue is the result. And you see there's a huge difference in terms of computation. It means that it can adapt with a less amount of data and very fast, because it's just only linear layer to adjust. And this is the case not just for one label, like one just for pleural effusion. For cardiomegaly, is the same behavior. For edema, the same behavior. And the consistent message is this. With less amount of data, you achieve much better performance and in much smaller number of flops. So to conclude, the post-hoc explanation allows the use of flexible black box, but then it leaves a lot of explainability to human and does not allow post-hoc explanation. It does not allow recourse. You don't like something about the model, you won't be able to fix it. Interpretable by design allows recourse, but suffers from performance. We showed a method that basically bridged the gap. You start with a black box, and you carve out the symbolic. We showed here the symbolic approach for us was first order logic, but in different approaches, in different domain, you may adopt different form of explainability depending on your application. For us, each of these was first order logic because they are highly interpretable and they are mimicking the decision making of the clinicians. And we also showed that with this method, we are able to transfer learn very efficiently, both in terms of computation and data. I did not show any result of intervention, but if the papers are here, but in the paper we also showed that if your model focus on a spurious features, the topic that I discussed yesterday, you can go back and intervene and fix that property, the behavior that you will not be able to achieve with the black box explanation. And that concludes my talk. Thank you very much.